Hello, grade 11s. So we're going to start right now talking about the mole. You've been introduced to the Factorlabel method, which will prepare us for um, this next topic on the mole, and more specifically, mole conversions, which we'll look at the end. But first, the concept of the mole. Okay, now normally I would have a video here for you to watch, so something a little fun to go through and your first experience of the mole, because I'll read this to you. I usually don't, but here it is. Found this a while ago online, someone reflecting on the mole. And they say the mole concept is one of the most feared and misunderstood concepts in all of chemistry. Many adults who cringe at recalling chemistry will tell you that they never understood that mole stuff. And the funny thing is about it is that the mole is really a very simple concept, and I think that many people never really understand it because it's not always presented clearly. If explained correctly, I feel that the mole can be an easy concept to master. So that's more of a challenge for me than it is for you. Let's hopefully try to go through this together as clearly as possible, and it should be okay. We'll see. Okay, first, the mole is similar to saying certain things like a dozen. So a dozen, 12 roses, or a dozen eggs, right? A gross has also a certain value. I believe it's 20, but we'll get to that in the next slide. Oh no, I think score is 20. Gross something else, not 20. If we count how many cupcakes we have, you'll see that we have 13. So in a baker's dozen, we have 13 cupcakes, right? Because the baker will then cut into one, see how one tastes or looks, and then sell the 12 dozen. Okay, and they score. Now here's a video of Sidney Crosby's 2010 Winter Olympics scoring on the Americans. Won't play that video right now, but that's just a score. Now all these words mean something, right? I'll go back to this, but they mean, hopefully I didn't skip over it. Yes, okay. So a baker's dozen means 13, a score means 20, a gross of something means 144. Imagine buying 144 eggs. Maybe not the best thing to do. So in chemistry, we use the mole, and this is the mole. It's 602 followed by all of these zeros, right? 21 zeros after that, or 6.02 times 10 to the 23. That's a big number. Now, for practical reasons and for mathematical reasons and the relationships we'll talk about later, this has to be big, because when we talk about the number of atoms of something, atoms are so tiny that it has to be a large number for it to be tangible, right? This is known as Avogadro's number, um, and like I say, for practical reasons, it has to be large. So it makes sense that you're going to buy 12 eggs instead of just a couple of eggs. Right, so atoms are so small, we need a large number. Let's move on. Okay, so there are, using Avogadro's number, and anything that has 6.02 times 10 to the 23 units, that will represent 1 mole. So one conversion factor that we'll look at is, now if you've seen the Factorlabel method lesson, you know that you've heard this already, the term conversion factor. You know that 6.02 times 10 to the 23, that being Avogadro's number, that's units. Now, units can mean anything. Units can mean number of atoms, number of molecules for every 1 mole. So those are our units here. So 6.02 times 10 to the 23 units for every 1 mole. Turns out there's a great relationship. Any mole, any 1 mole, so 6.02 times 10 to the 23 moles of 1 mole of hydrogen or beryllium, helium, that number of particles of any of these elements will actually equal the atomic mass. So here, helium has an atomic mass of 4.003, but we'll just say 4. Now we've usually seen that as 4 atomic mass units. Turns out that if we have this many number of atoms of helium, it will weigh 4 grams. Isn't that great? 4 grams for every 1 mole of helium. And that also goes for every other element. So we look at beryllium. If I can see that clearly, it is 9, I believe, 9.012. Might be wrong there. My eyesight might be failing me, but it's 9, let's say. 9 atomic mass units right? But 1 mole of that is actually 9 grams, right, for every 1 mole. So that great relationship exists there. So this allows us to use mass numbers on the periodic table, right, also known as atomic mass or AMU, and to figure out that there's this new number, really not new, but just new name for it now, called the molar mass, right? It's the mass of an element for every 1 mole. Okay, we'll get more into this. So here's our example. So if we have this many atoms of carbon, so 6.02 times 10 to the 23, this is superscripted, right? So a little line up here, um, arrow up here. If we have this many atoms of carbon, right, in the periodic table, it'll say 12 atomic mass units. It'll actually weigh 12 grams. We've talked about helium, copper. If you have this many atoms, 6.02 times 10 to the 23 atoms of copper, it'll actually weigh 63.5 grams, which is the mass of copper. So we now have this new term then, the molar mass, which is equivalent to saying atomic mass, right? Here's a misunderstood concept. The question often can be, I thought that 1 mole is always 6.02 times 10 to the 23, and yes, although it is 6.02 times 10 to the 23, that refers to the number of things or the number of units, right? Units, again, units can be atoms, as we've talked about just now. We'll see later on that it can be molecules, right? So yes, it is always this, but we have different masses because, as you know, we have different atomic masses for each element. Going back to our first unit, we figured out how to calculate the average atomic mass, which takes into consideration all of the isotopes of each element, right? So every element has a different molar mass, same number of atoms per mole of it, but it will have a different molar mass because it just weighs differently based on all of its isotopes, number of protons and neutrons, right? So let's move on. All right, so here is a partner question. Since you're working at home, it'll be a self question here. So an unknown element has an atomic mass of 20 units. Okay, so the AMU is 20 units. If there are 2 moles of this element, how many grams would you have? Right, so let's see. If we have 1 mole is equal to, oh, this, by the way, MOL is a short form for MOLE. I know scientists are great. So 1 mole is equal to 20 sorry 20.0 units. So if we have 2 moles, how many units is that? Well, it's going to be double that, right? 40 units. And because you know that 1 mole is actually equal to its molar mass, or grams for every 1 mole, so that means 2 is also going to be double that. 2 moles in grams is going to then be 40 grams, right? So we have 40 grams in 2 moles of this element, right? 40 grams. That conversion was pretty simple. We could have shown the math. Didn't quite show the math here, but we'll get into more complicated examples in just a minute. Okay, again, I just took some screenshots of a periodic table. You can see that copper has that atomic mass or molar mass, boron 10.8, oxygen roughly 16. From your periodic table, we can then calculate molar masses, or not just calculate, but simply read, figure out what these molar masses are for each of the elements. What we can also do is we can see that if we can figure out the molar mass of one, in this case 1 mole lithium is equal to 6.94 grams, right, straight from the periodic table, nothing you have to memorize. This is expressed as these units we've gone over, right, grams for every 1 mole. What are the following molar masses? So here we have sulfur dioxide, right, we have copper borate, not quite copper borate, copper 2 borate, right? So I got straight into the first example here. Sulfur, straight from the periodic table, has a mass of 32.06 grams. Right? Now, to figure out the molar mass of sulfur dioxide, we're going to take that 32.06 grams per mole from sulfur, or of sulfur, and we're also going to add, because we have 2 oxygen, you're going to have 2 oxygens where each one weighs believe oxygen has a molar mass of roughly 16 grams per mole. So that's going to be 32, right? We're just multiplying that by 2, 32 grams per mole. So all we do is we take 32.06 plus 32, and we'll get the molar mass for sulfur dioxide. Now I'm going to erase this so I can make room for the answer, right? But essentially it's just these two numbers, right? So let's erase that and see what the answer is. 64. There we go. So 64.06 grams per mole for sulfur dioxide. So this is the first time we've seen now that we've calculated that what the molar mass is, not just for an element but for a molecule. Okay, next we have copper 2 borate. Okay, we're going to break this up. So we have copper. Copper has an atomic mass, a molar mass of 63.55. There are 3 of them, right? There's a subscript right here. We have 3, so we take the molar mass of 1 copper, multiply by the 3 coppers that exist, and we get 190.65 grams per mole. Right, we're going to do the same thing for this borate ion. So this subscript tells us that there are 2 borates. We can break that up into 2 borons and 6 oxygens. So each boron has a molar mass of 10.81. There's 2 of them, so we get 21.62. Again, same units, grams per mole. Right, for every 1 borate, there are 3 oxygens, but because we have 2, there are now 6. So we get this. 16 is the molar mass for oxygen, times 6, we get 96. Again, the same units. All we do is add these up, and we get a total molar mass of 308.27 grams per mole. And there you go. Let's erase this. That's our answer there. Right? Okay, so that's how we can calculate molar mass. Okay, this next part. Now, if we're given a mass of something and then asked to convert to the number of moles, we can do that. Also, if we're given moles of something, we can convert that into grams. Now, this is where the Factorlabel method comes in play. I'm not going to show you that formula triangle, rather you understand how to use a Factorlabel method. I will show you a formula, and I suppose you could figure out your own formula triangle, but we're going to avoid that. Okay, so I'm clicking on the wrong thing here. Okay, so just to review some symbols, N represents, well, I'd have to write this down, but N represents moles, which is also sometimes abbreviated like this, MOL. Okay, next thing is molar mass. Now, I like to show that molar mass symbol is capital M, capital M. Okay, mass is M, and that's going to be in grams. Okay, and here is your formula. So moles are equal to mass divided by molar mass. You can use this, feel free. We're going to do it both ways. You're going to use the formula and use the Factorlabel method as well. And my captions are just keeping up with me, so I think it might be going too fast for it. Give it a second. Okay, I'm going to switch screens now. Hopefully you're not experiencing this. I know my captions are hiding it, but hopefully you're okay so far. We will get into some examples, so hopefully this will be able to tie us all together. I'm going to end my presentation right now. I'm going to discard notes here, and let's see, this will just take a second to load. But I have 3 questions I want to go over. Don't do that right now. Okay, so that color will do. Yeah, that color will do. Okay, question 1. many moles are there in 50 grams of carbon? Okay, this method we're going to use a formula. Okay, where moles is equal to mass divided by molar mass. In our next example, we'll use a Factorlabel method. Okay, so back to solving. Okay, so we need to figure out moles. We're given mass. What we're not given, and you have to just use your periodic table, is the molar mass of carbon, which is 12 grams per mole. Right, keep your units very important. So now we have moles are equal to 50 grams divided by 12 grams per mole. Notice grams cancels out, grams cancels out, and we're left with, just round it here to the nearest tenth. We'll talk about significant figures and digits later, but round to the nearest tenth, and we have 4.2 grams. Sorry, let me erase that. Not grams. Grams canceled out, right? So it's moles. 4.2 moles. So that's our answer. 50 grams of carbon is actually 4.2 moles. Next question. How many moles are there in 24 grams of iron 3 chloride? Okay, so how many moles are there in 24 grams of iron 3 chloride? Now we're going to use, instead of formula, in this example, we're going to use the Factorlabel method. Okay, so let's solve. Right, now the general form of the Factorlabel method, if you recall, is write down what you need. So here the question's asking us for moles, so we're going to write down number of moles. Okay, we don't know what the number is. We're going to write down the unit because that's what the unit we need. Then we write an equal sign, right? So the general form of the Factorlabel method then asks us to write what we're given. Okay, so this we're given 24. So 24 grams of iron 3 chloride is what we're given. We're going to multiply that by a conversion factor. So this conversion factor has to have the unit we want to get rid of at the bottom. That's grams, right? Because grams are going to end up canceling out. And the unit we want to keep, which is this unit here, moles, at the top. Then we have to ask ourselves, if this here is our conversion factor, then where do we get this number? Now look at these units. Moles or grams over moles. That is actually, it looks like the molar mass. So we need to figure out what the molar mass of iron 3 chloride is. That's a 3. And if you do that, you have the molar mass of iron plus 3 chlorines. You're actually going to get, I have it written down here, 112.84 grams per mole. So there are 112.84 grams for every 1 mole. So that doesn't really match what's happening here. But this is where you have to interpret and figure out what to do. So the number that's associated with the unit mole is 1. That looks kind of messy. Okay, the number that's associated with the unit mole is 1, because if we interpret this properly, it says 112.84 grams for every 1 mole. So we write 1 mole. How many grams are there for every 1 mole according to the conversion factor? It's 112.84. So what we're doing here is we're canceling out the units we don't want and we're keeping the unit we want. Turns out we're taking the mass and we're dividing by the molar mass, which if you look at the formula, that's exactly what you have to do. Okay, so if you do that, your answer is going to be rounded to the nearest hundredth in this case. Again, we're going to go over significant figures. It's 0.21 moles. So that is your answer. Okay, so 24 grams of iron 3 chloride. converting that to moles is actually 0.21 moles. Okay, so I'm going to here again take a picture, screenshot, go back, rewind. Last question though. We're going to use the Factorlabel method again. Here's the last question. Again, feel free to take a break, pause. How many atoms of CO2, usually a gas, are there in 2 moles? This might be repetitive or redundant, but I'll say it anyways, of CO2. Okay? All right, so Factorlabel method. When you don't know what to do, Factorlabel method will really help. Another mantra that's often repeated in class is when you don't know what to do, convert to moles. Right, well, you already have moles, so let's just continue. We'll practice lots of these, but let's start placing or completing the general form of the Factorlabel method. So the question asking us for the number of atoms. So let's write down, we need the number of atoms. Okay, equal sign. Then what are we given? Right, we're given 2 moles. So 2 moles of CO2. Okay, we're going to multiply that by a conversion factor. Don't know what that conversion factor is yet, but let's figure out the units. That'll give us a clue. We want to get rid of moles. Okay, let's get rid of moles. So that goes at the bottom. The unit we want to keep is atoms, number of atoms. Okay, so that's going to go at the top. Okay, so what conversion factors have we seen so far? We've seen molar mass, and that's in grams per mole, or moles over grams, same thing, right? We're just flipping them. That's not it. This can't be it, right? That's not it. Okay, we need something that has atoms per mole, or number of things per mole. Turns out that our conversion factor is actually Avogadro's number. Okay, so Avogadro's number, if you recall, is 6.02 times 10 to the 23, and how you saw in the lesson was units for every 1 mole. Okay, now this term units is an important one. This can mean many things, right? In our case, it's going to mean atoms. So let's erase that. We have 6.02 times 10 to the 23 atoms for every 1 mole. Right, now let's complete this conversion factor. What number is associated with the unit atom? Well, it's this, 6.02 times 10 to the 23. For every how many moles? Well, there's an imaginary 1 here, so it's for every 1 mole. So what we're really doing here is taking 2 and multiplying it by that. Notice that your mole cancels out, and we're left with, well, here we're just multiplying it by 2, so it's 12.04 times 10 to the 23 atoms. So that is our final answer. We figured out then that in 2 moles of CO2, there's 12.04 times 10 to the 23 atoms. Okay, so those are our 3 examples for today. We're going to continue with mole conversions practicing. Later, going back to our PowerPoint presentation, I'll start it again. We only have a couple of slides, but nothing too much to do here. So this we would have normally done in class. Feel free to go over this yourself. Answers are all here. Here is just a table, and there's really nothing to do on this column. Here, if we're given moles, we have to figure out molar mass always using your periodic table. You won't have to memorize any of these. You can use Factorlabel method or moles equal to mass divided by molar mass. Right, and then back to grade 9 math, you have to be comfortable to rearrange this formula. So here we're being asked for grams. Well, that means rearranging this formula back to grade 9 math just means moles times molar mass. So moles times molar mass. You do that and you'll get 9.1 grams. Right, so practice this if you'd like, test yourself. This is posted online for you, and that's it. Your home fun is here. Check out question 12. We can take this up. Any questions, let me know.